Hey everyone, in this video we're going to go over how to find roots algebraically given a quadratic function. So this should be something that we're pretty up to date with, being that it's the most recent topic featured on the quarterly. Obviously we've learned more advanced ways to do this, quadratic formula, completing the square, CTS, um, and this is going to go all the way back to one of the easier strategies of factoring. The quadratic that you will see will be factorable, which is nice, but I will offer some alternatives if you don't like factoring for some weird reason. All right, so first of all, you really have to understand what roots are here, because if you don't know what it's asking when it says determine the roots, you're really not going to know the first step, which unfortunately is going to lead you down the wrong path. So roots are where the graph, if we want to think about this visually, where the graph, and this isn't saying that this is what d of x looks like, but it's where the roots hit the x-axis, or where the graph hits the x-axis. Okay, in other words, where y equals 0. Okay, another word would be the x-intercepts. All these are synonyms for one another. X-intercept, the zeros they're called, or more commonly as you get older, roots. So our first move is actually going to be setting this equal to 0. I want to know, when is that output d of x going to be 0? We're going to algebraically determine this. The first thing that I notice, always be aware of this, I see 8, 4, and 40 right away. I say, hey, these are all multiples of 4. Obviously 0 can easily be divided by 4. I'm going to make my life a little bit easier. Always be on the lookout for that. Okay, so let's try a factoring strategy here. We could see, even though we got rid of a GCF, we're going to have an a greater than 1, which is what I call an eyeglass. So our product is going to be not negative 10, but 2 times negative 10, or negative 20. Our sum is still going to be the positive 1 in the middle. The sum never changes. So we're looking for two numbers that accomplish this. Okay. Negative product means we have one positive and one negative. And they do have to be 1 apart. Playing around, 10 and 2, 20 doesn't have that many factors. You'll eventually arrive at positive 5 and negative 4. And there's a few ways you can interpret how to do this next step. I'll show you both. Some people like to do it this way, factoring by grouping. I'll show you how both end up getting you the same result. So now I'm factoring on the GCF on that left-hand side. Put little like brackets here. That's going to be 2x plus 5. GCF, factor out the negative if the lead coefficient's negative. For 4 and 10 is 2. Also 2x plus 5. If you did this correctly, the bubbles should match. You factor out the common bubble, and then what I call the leftovers. Okay, so we'll pause right there. And now another way, some people jump once they find the two numbers. This would be commonly referred to, I call it like trash, which hopefully won't describe how you do with this question, but just the fact that we're throwing out a GCF. So you don't want to say equals. In the past, some students have gotten a little annoyed that I will take off for this. Okay, that's just not understanding the equivalency there. Obviously, that's not going to be equal to 2x squared. So it's just kind of a middle technique. Now, whatever it starts with, that's why I put 2x. So it was 2x squared, I put 2x and 2x. I still put the numbers in there. We see the 5 and the negative 4. And now, similar to what we did with the factoring by grouping, we're looking for GCFs, and in this case trash because we're throwing them out. Okay, so there's no GCF for the binomial on the left. There is a GCF for 2 on the right. So usually when we divide out a GCF, that's why I call it trash, we kind of keep it there. In this case, we literally throw it away. We don't care about it anymore. And obviously we notice either technique brings us to the same end result. So it doesn't matter which one I roll with here. I'm going to set each of these binomials equal to 0. I get x equals 2. I get 2x equals negative 5. Or x equals negative 5 halves. So those are our two roots. I'm horrible at making brackets. -2.5 or -5/2. Usually just squiggle a line and pretend that it is a bracket. We don't want to put those in parentheses. That would look like a coordinate. And you could write this a few ways. Even just stopping right here and circling it would be sufficient enough. Now, checking wise, we didn't mention this earlier. Algebraically means we want to show all this good, nice work. You could obviously check on the graphing calculator. You'll see this pretty clearly in your table. This, you can play around with the delta table, what your table goes by. It is a half. So you could just simply make your calculator go by halves. Or you could use the 0 function, which is typing it in, second trace, choice 2, 0, that's where you get the left-right cursor that we've talked about. So what would that be? -2.5. This is the one we'd probably have trouble seeing. You would want to hit left over here, right bound, and then your calculator is going to find the root between those two. So a lot of options for how you can check this. I would say probably if you are comfortable with doing it, checking on the table would be the fastest. Remember when you go to your table, if you hit the plus sign, you get this little guy on the bottom. Really, that's saying delta table. Like, what do you want your table to go by? Traditionally, it's on 1. That's why your table says 1, 2, 3, 4. So if you just change it to 0.5, now you'll see this root that is at a 0.5. It's -2.5. Your calculator is going to go by halves all the way across. It's not just going to have the one in there that you want. So you still have to scroll a little bit, but you will see it. All right, and like I said, I did want to offer one alternative. So I showed you both factoring strategies, whether the factoring by grouping or the trash. But for people that don't like factoring at all, I would not recommend this. Factoring obviously is your best or most efficient would be a good word to use, but technically speaking here, we could do quad formula. Quad formula is a universal tool, so it will always work. Just obviously a little bit more work than you need here. So in this case, A, B, C. So my B is 4, which is going to be -4. That's going to be 2 times 8. And if anything, hopefully this little interlude will show you to maybe try factoring rather than this. And this is -40. Okay. My radicand, I have a 16 as a denominator. My radicand is going to be 16 minus, I forgot to close the parentheses there, 32 times 40. Let's see. We have, should be a perfect square underneath the radical. Yep, it is. How do I know that? We got rational answers, which means we shouldn't have any radical left over. The square root of 1296 is going to be 36. Now, some of you guys like to stop here with the quad formula. We could do the math. There's no radical. So you're going to do -4 plus 36, or -4, excuse me, minus 36, which is going to be -40. So you're doing kind of both the positive and negative separately. Obviously, this is how we get our answer of 2. And with this one, this is how we get our, if we divide out a common factor of 8, that's how we get our 5/2, or 2.5. So a lot of alternatives. If you're not a factoring person, that's one way of answering this question. Could be a little bit more work, but the options are there. And as with factoring with quad formula, we could check on the calculator a few different ways. This is Finding Roots Algebraically. Thank you for watching, and best of luck tomorrow.